I've worked a quick example for you on page 271. It tells you to find the zeros of the functions by factoring. I am going to give you one of those problems to try factoring. I did problem B with you. It's a fourth degree polynomial. So I know that the fundamental theorem of algebra says I'm going to have 4 roots. So I'm going to start my factoring by first of all recognizing that this is a difference of 2 squares. This is a perfect square. You get x to the fourth if you multiply x squared times x squared. 16 is a perfect square. You get 16 if you multiply 4 times 4. So it's going to factor by the difference of 2 squares method by putting the roots in the parentheses and putting a plus sign in one and a minus sign in another. You then want to continue factoring. This one right here is, again, a dots problem. It is also a difference of 2 squares, so it factors again. This one is a sum of 2 squares. We don't have a rule for factoring the sum of 2 squares, so it stays that way. We use the zero product property. The zero product property says that if we've got factors and they're equal to 0, then we can set each factor equal to 0 and solve. So I subtract 4, take the square root of both sides. The square root of -4 is plus or minus 2. Set this x plus 2 equal to 0, subtract 2 from both sides, set x minus 2 equal to 0, add 2 to both sides. And the final conclusion is I have 2 imaginary roots and I have 2 real roots. That means this problem will cross the x-axis twice. It will cross it once at -2. It'll cross it a second time at +2. And then the other 2 of the 4 roots that the fundamental theorem of algebra says it has to have are imaginary. So in total, it does end up having 4 complex roots, 2 imaginary roots, 2 real roots. And we could take each one of these roots and turn each one of them into a linear factor. And so this would be x plus 2 and x minus 2. So just like the Springboard book said, you can, all fourth degree polynomials can be written as 4 linear factored terms, linear factors. So we have proven the fundamental theorem